So the other time we had looked at some the general introduction of projectiles. We looked at how to determine the position and the velocity of the particle at any time t along the trajectory. So we looked at the equations for the horizontal motion and the equations for the vertical motion. So today we are going to look at the general definitions like the maximum height, time taken to reach maximum height, the horizontal range, and then the maximum horizontal range. That's going to be enough for today. The equation of the trajectory, we shall look at it next time. Then let us have also a glimpse on the vectorial approach. A glimpse on the vectorial approach. Remember, we are still looking at particle being projected in space or in air with a certain velocity u at an angle theta to the horizontal. At an angle theta to the horizontal. That's the basic thing that we are looking at under projectile motion. Yeah, but before that, I learned that you have been introduced to differentiation and integration. There are some things I want to put here, then we note them somewhere in our mind. I shall refer to them sometime later, but I want you to, I was waiting, say that I was waiting for paper one teacher to take you through the introduction of integration and differentiation you had learned, but now integration. So these ones, you can note them somewhere. They shall be of help. So you know that acceleration is dv/dt, right? You know that velocity is the s dt. I'm just writing them because I know that you learned them in paper one. Somewhere they shall be of importance. And if acceleration is dv/dt, then it means velocity is the integral of acceleration with respect to time. Am I right?
Yes, teacher.
Then if v is equal to ds dt, then distance is the integral of velocity with respect to time. So put those equations somewhere. I shall just refer to them. Put them somewhere. So we go, let us introduce some bit of vectorial approach such that we work out comparatively. There are two methods that we can use under projectile motion. The other time we learned that, I can wrap up this one, but I told you that take a note, somewhere they shall be of help. The other time we learned that if I throw a body in air with the speed u at an angle theta, I can easily determine the position of the body at any given time t. Position of the body at any given time t, I can call it s a function of t, position of the body at any given time t. I can also find the velocity of the body at any given time t. I think we looked at those ones. Then the velocity of the body at any given, from the velocity of the body at any given time t, we can derive the speed of the body at that instant. The speed is the square root of the what? Is the magnitude. Magnitude of the velocity at that given time t. We looked at that. So now let us introduce in some bit of Let us introduce in some bit of vectorial approach. If I have my initial velocity as u, then it means that horizontally we have a unit vector I, and then vertically we have a unit vector what? Unit vector j. So in the unit vector I, what is going to be u? In the unit vector I, u is going to be
U.
or I can simply call it
U cos.
u. Unit vector I corresponds to the x-axis. Then that of j corresponds to the y-axis. Any question? Somebody has a question? So horizontally, if I decide to resolve this initial velocity, horizontally it is going to be u cos theta I. Call that equation 1. That okay?
Yes, teacher.
Then vertically, it is going to be, how can tell us vertically how it is going to be?
U sin theta.
U
Sin theta j.
U sin theta j. U sin theta j. Very good. So it means that the initial velocity, if I combine equation 1 and 2, the initial velocity u cos theta I plus u sin theta j. Is that okay?
Yes.
Yes.
Yes, teacher.
So that is how we can represent the initial velocity in I and j notations.
Maybe,
so keep this equation,
Mr. Wakaya.
keep it aside. So then let us find the velocity at any given time. Yes, sir. Theodore.
I don't know if you could help them as well write it in column form so that we understand that as much as we can write it that way, we can as well put it in column form. Eh?
Pardon?
Can you as well express that initial velocity in column form?
Oh, in column form.
Yes. So that
yeah,
we are having
so
u
in column form it can also be u. Column we start with I, yeah? Cos theta, and then u sin theta. Is that okay?
So what is u?
Now, this one is the initial velocity expressed in I and j. Now, this u cos theta stands for the horizontal component, and then u sin theta stands for the vertical component. But the combination, which is represented here, is the u, the initial velocity. Instead, it is expressed in I and j. We are now trying to bring in the vector approach. Not yet fine?
It's fine now.
Okay, I guess one thing that the girls need to understand, they are given an initial velocity, you can express it in the vertical and the horizontal component. And that is what basically Mr. Wakane is trying to do. You resolve it. You resolve the initial velocity in the vertical to get its vertical component, and you resolve it in the horizontal to get its horizontal component. So basically, it's about resolution. You just need to remember your knowledge of resolution of the system.
So this U resolve U horizontal is going to be what? U, hope you can see it. U cos theta. Then vertical it's going to be U sin theta. Do you see that? Can you able to see that?
Yes, teacher.
Yes, we are simply resolving, finding the horizontal component and the vertical component. Then we are attaching the horizontal component to the I and the vertical component to the J. To have our initial velocity in that format of I and J. I don't know whether this one is visible. I hope it is visible. Let us now derive the acceleration. Let us try to derive the acceleration. We have just seen that the initial velocity can be given as U sin theta, U cos theta, and then U sin theta. Or initial velocity can be given as U cos theta I plus U sin theta J. We note that one somewhere. We go back to our velocity at any given time t. Velocity at any given time t, we recall. Yes. Recall that velocity is given by U plus at. Velocity is given by U plus at. Vertically, our velocity is going to be, we look at this, U sin theta J. I'm putting J because we are considering for vertical motion. There is U sin theta minus dt, then into J. Is that okay? We looked at this one the other time.
Teacher.
We looked at this one the other time. I'm just adding the unit vector J to show that we are looking at the vertical component of the velocity. Then horizontally, we are deriving something that looks like U cos theta. We are using this equation. We said that acceleration is 0. That's why I'm stopping here. Then I add a unit vector I. So vertically, we have a U sin theta. Acceleration becomes a negative d, then times a t. Horizontally, x is going to be U cos theta, and then a unit vector I. Is it okay?
Yes, teacher.
So
Yeah,
if
it's
we have
not.
Vy and we have a Vx, then we can find the speed. The speed is
Someone
obtained.
has said it too. It's not okay.
Someone has said it's not okay. Okay. Here I have just noted these ones because we derived them the other time. We say that velocity is equal to u plus at. But remember, when we are dealing with the projectile motion, I told you the other time that we divide the motion into parts, the horizontal and the vertical. So we are using our first equation of motion and want to find the two velocities. Velocity corresponding to the horizontal motion and then the velocity corresponding to the vertical motion at any given time t. So if this is my formula, then I shall horizontal motion as Vx, which is equal to initial velocity. We had looked at it as u cos theta. Then plus, by the other time, that horizontally acceleration, which now changes into acceleration due to gravity, acceleration which now changes into acceleration due to gravity, it is not there horizontally. It only acts when we are dealing with vertical motion. So if I'm dealing with horizontal motion, then this shall be acceleration due to gravity, which is a 0 times a t. So my horizontal velocity at any given time t is going to be u cos theta. So you realize that the horizontal motion at any given, the horizontal velocity at any given time t is the same horizontal component of the initial velocity. Note that one somewhere. That at any given time t, that the horizontal velocity is the same as the initial velocity, the horizontal component of the initial velocity. Sorry, let me repeat. You realize that the velocity at any given time t, the horizontal component, is the same as the initial velocity, horizontal component of it. Does it make some sense? Eh?
No.
We have said that velocity x, the horizontal component of the velocity horizontally at any time t, where there is u, initial velocity. Remember, initial velocity was given as u cos theta. Is that one okay?
Yes.
Yes.
Initial velocity was u cos theta horizontally. Then horizontally, the other time we learned, I don't want to repeat this one. We shall be repeating the whole of the previous lesson. Acceleration due to gravity horizontally is 0. So if I substitute 0 for acceleration, then I substitute u for u cos theta, you realize that the horizontal component of the velocity at any time t is u cos theta. So it remains the same as the initial velocity. Is it okay?
Yes.
Yes.
Now, vertically, hope we can see here. Vertically, still using v equals u.
Yes, teacher. Yes.
U, initial velocity was u sine theta. Acceleration became a negative v, then times a t. So our vertical component of the velocity now becomes in vectorial approach. We simply attach a unit vector j like that. So those are the two the examples or in the questions, you will say continue.
Yes.
Okay, let me first pause that. Then we go to our definitions. Definitions, we need to look at the maximum height. There is the maximum height. Remind me. Time taken to reach maximum height, and then the horizontal range. So let's begin with maximum height. Supposing a body, I think you can see here. I'm able to see here.
Yes.
Yes.
Supposing a body is projected with initial velocity u at an angle theta horizontal. So it comes back and falls on the same ground, on that same horizontal ground. A point is reached when this body is making a U-turn. In other words, a point is reached when it has reached its greatest or highest point, and now it is making a U-turn, coming back. Like we saw in motion under gravity. At a point where the body is making the U-turn, it is coming back. The vertical component of velocity is 0. Its velocity at that point is 0, not so?
Yes.
So, if Vy is 0, and we derive the Vy as, how did we derive Vy? Vy was what?
U sine theta
U sine theta
minus
Twice.
minus
Minus.
gt.
Minus
minus
GT.
But let's say at maximum height, we have started with maximum height. At maximum height, the body is momentarily at rest. That's why we say that its vertical component of that velocity is 0 at that point. So if I substitute 0, I'm going to get, where there is Vy, I get U sine theta minus dt. So putting dt this side becomes a positive. If I divide by b, I shall get my U sine theta divided by g. So that's our time taken to reach maximum height. Is that okay?
Yes.
Teacher,
So we go to the maximum height itself.
teacher, I have a question.
That is time taken to reach maximum height? Yes.
At maximum height, is Vy also 0?
At maximum height, it is Vy that is 0.
Vx is not 0 at maximum height.
At maximum height. Because vertical motion, because we are dealing with vertical motion or vertical part of the motion, the body. Let's see how this will be. Horizontal, we say that Vx is U. This was the equation for horizontal component, not so?
Yes.
So if you are looking for time, how would you find it using this equation? Is there a time anyway?
No.
No.
I don't know whether I have answered her.
Yes, you have answered.
Maximum height itself, we can use v squared equals u squared plus 2as. That's our general equation, the third equation of motion. So we can substitute Vy. Now put this equation in our projectile to suit our projectile motion. The u becomes vertical. U becomes u sine what? Sine theta minus 2g. S becomes capital H, the maximum height. Yes, Adija.
No, nothing, teacher. It's okay.
So at maximum height, we say that maximum height velocity is equal to 0. So if I substitute 0, I shall get u squared sine squared theta minus 2g h. So I put the 2g h this side, I get u squared sine squared theta. When I divide by 2g, h becomes u squared sine theta over 2g. Is that okay?
Yes.
Yes, teacher.
Okay. So that's how we come up with the maximum height, formula for maximum height. Then horizontal range. Horizontal range, we say that to a point where the body lies on the same horizontal, on the same horizontal what? On the same horizontal ground. Is it okay? So if I call this one as my point is here, the other time I gave you a simple trick that you can consider. Are you able to see the diagram?
No.
See here?
Mr. Wakan, I think you have to adjust your camera. John?
There.
Yeah, that's better.
Is it okay?
Yeah, that's better.
Yeah.
Okay. So the other time I told you that we determine the position of the particle at any given time t on the trajectory. The trajectory is this path taken by the particle, this curve is what we call a trajectory. So if a particle is at any point, we learned the other time that its position can be, start with x and then y. We say we are calling this one point P, where x describes the horizontal component at any time t, y describes the vertical component at any time t. But there is the other time something that we learned, that if a body comes from here and then reaches here on the same horizontal ground, the vertical displacement, there is horizontal displacement, which in this case, horizontal, it has run a distance, capital R. But vertically, displacement is 0. You remember that?
Yes, teacher.
So, I have used the word vertically, displacement is 0. You quote that statement. Vertically displacement is 0. So because of that statement, let me use the vertical component. If I use S equals ut plus a half at squared, we substitute this equation to suit our projectile motion. We shall get vertically it would be y equals u. What's the vertical component of the initial velocity? Sine theta, then times the acceleration becomes a negative g, then times t squared. I hope we are following. So if a body comes from here, then comes to the same horizontal ground, vertical displacement is 0, sine theta. That time I can call it capital T, which is now going to be described as the time of flight. We shall look at it. Time of flight, okay. In fact, we can even first find the time of flight, then it shall guide us to the horizontal range. Is it okay? Let us first find the time of flight, it shall guide us to find the horizontal range.
Yes.
Yes?
Go on.
Minus a half d t squared. Horizontal range, I would use the horizontal component of that displacement. But no harm, I can also finish up this one. Then it shall guide us to find the horizontal range. So this is what we have. Capital T is the time of flight, which is the time taken for the particle from point A to point B. So this one is going to be u sine theta minus a half g. Minus a half dt, then into t. Can we see that?
Yes, teacher.
No.
So either, let me write here. So from this equation, we see that either capital T is equal to 0, or the whole of this bracket is equal to 0. Or the whole of this bracket, which is u sine theta minus a half dt equals 0. From the second equation, I think I can make capital T the subject. I can have u sine theta equals dt out of 2. So if I cross multiply, I get what? Those who are following.
2u
Sine
sine
theta out of G.
theta
Out of G.
Equals. So that is the time of flight. This one is the time taken. Time of flight is the time taken that we realize that we have two values of time. We have capital T is equal to 0. That is the time at the starting point. Particle has not yet been what? Thrown. Is that one okay?
Yes, teacher.
Then this Gen expression is the time taken at point B, where the particle lands on the same horizontal ground. Is it okay?
Yes.
Ananda?
Yes,
Yes.
teacher.
Is it fine?
Yes, teacher.
Gift.
Yes, teacher. I wanted to. Okay, I realized that the time of flight is twice the time taken for the body to reach the maximum height. I don't know if that assumption is okay.
Hey, yeah. It's something that we go. I want to rub off. I'm using the same board. So I expect some of you are taking note. Yeah, thank you for that. What do you deduce? What do you conclude from this? From t equals 2 u sine theta over v. Do you realize that the whole of this one was small t? Do you realize that?
Yes.
No.
The whole of that I have circled was small t. It was small t was the time taken maximum height. So we can also conclude from this equation that time of flight is twice the time taken to reach the maximum height. Yes, Tendo Esther.
Teacher, I'm saying it's okay.
Okay. Let me check for some let's see. Faith. Faith, where are you?
Yes, teacher.
Is it okay?
Yes, it's okay.
Kakai. Kakai is asking. I knew that Kakai must be asking now. So we have derived, let me check here. Let me check. Nkwanzi.
Yes, teacher.
What have we finished so far? We have derived the time of
flight.
Another one.
Time taken for the body to reach the maximum height.
Very good. Another one.
Maximum height.
Maximum height. So, like I told you that the time of flight, capital T, we have gotten it as what? Rina, we have got capital T as?
2u 2t.
The general formula.
2u sine theta. G.
Out of G. So we keep this one somewhere. We are going to use it. Now let us consider the horizontal displacement, the range. Horizontally, still from S equals ut plus a half at squared. Horizontally, I called my horizontal component R. The U is going to be U cos theta times T, which T now has become the time of flight, plus, plus what? Another, plus what? Here. Plus what?
Zero.
Very good. Plus 0. I knew that Ananda must be asleep now. I don't know what happened, but she's asleep. Some of you are attending the lesson in the bed. Can you wake up? So U cos theta times T. I'm using capital T because I'm considering to point B. So my horizontal distance has become the capital R. My time has become capital T. Horizontal, we say there is no acceleration. That's why I'm leaving it at that. So if I have R as U cos theta times time.
What is range?
Yes?
What is range?
What is range?
Range is distance.
Range is the horizontal distance covered. Horizontal distance covered from point A, the point of projection, to where the body lands on the same horizontal ground. Is it okay? This horizontal distance covered is what we are calling the range.
Yes.
And the corresponding time, we are using capital where the body lands. Remember, capital T had two answers. Had when time is 0 and when time was this expression. When time is 0, I told you it is when the particle is at point A, just before being thrown. Then when time is this expression, it has now reached the landing point on the same horizontal ground. The other thing that we must note, when the particle reaches the landing point on the same horizontal ground, I'm emphasizing that time is going to come when they tell you that a particle is thrown from point A and it passes by the level of projection. Either stops somewhere in the air or falls below the level of projection. Do you get that? So such questions are going to arise. But here we are considering that from point A to point B on the same level ground. So if I substitute for capital T was 2U sine theta out of D, you get what?
U squared cos theta sine theta.
U squared times, I want to rearrange this 2 sine cos, 2 sine theta cos, the whole of it out of D. Are you seeing the mathematics I've done there? Hope you can see. Have you seen the mathematics I've done here? U times U squared, then 2 sine theta cos theta. But from trigonometry, this one gives you what?
Sine 2 theta.
Sine 2 theta.
Sine 2 theta.
Sine 2 theta, the whole of it over what? So that's the formula for horizontal range. Yes, Ashley. Ashley?
Yes.
I have a question.
No.
Okay. So that's the formula for horizontal range. I'm rubbing off. You write it somewhere. We are starting right now.
Teacher?
I'm rubbing here. You have a question?
Does it mean that for horizontal movement, the vertical displacement is 0?
Eh? But you have a very good question. If I'm trying to get what you're saying, I hope you are following. When I was finding the time of flight, capital T, when I was finding time of flight, capital T, I considered the vertical displacement of this equation. And the vertical displacement, I let S to be 0. That's at a point when the body has reached point B. So when S was 0, U was U sine theta times capital T minus a half D, that is vertical displacement. So that one gave me the time of flight. I considered vertical displacement. It gave me the time of flight. Then when I was finding range, I used the same equation, but I considered the horizontal displacement. Horizontal S becomes capital R, U becomes U cos theta. Now T becomes capital T. Horizontally, there is no acceleration due to gravity. This is how I have used the same equation, but the first part gave me the time of flight. The second part gave me the horizontal range. Is that okay?
No.
Yes, teacher.
Yes, teacher.
First part gave me the time of flight. When I got the time of flight, it was simply to substitute it in the horizontal. To substitute it the same equation horizontally. This will be x equals U cos theta T. There is an acceleration horizontally. It stops at that. But saying that, x changes in capital T. So you just substitute obtained from this equation. Then you find expression for capital R. Carla?
Yes.
Is it okay? So we have derived the range as U squared sine 2 theta out of D. When you throw a body from point A to point B, you must have seen that there is a time when you throw a body. I want us to be practical here. There's a time when you throw a body. When you throw a body vertical at an angle of 90 degrees, it comes back to the same ground, to the same point of projection. So when you throw it at a certain angle, when that angle is very big, there is a certain distance it covers. When you reduce the angle, the distance increases. Reduce the angle, distance increases. Time comes when you reduce the angle, distance reduces instead. Have you ever noticed something like that?
Somehow.
Yes.
No.
Yeah. If not, then try it out. You go after the lesson, you get a stone, you start throwing it. When you throw it at a very big angle, when I say angle now, you know what I'm talking about. When you throw it at a very big angle, it is going to land nearer to you. You reduce on the angle, it falls further. You reduce the angle, falls further. Time comes when you reduce the angle, now it starts coming nearer as you are reducing the angle. So it means that there is that angle when you throw the body, it lands the farthest. Rachel? Rachel?
Okay.
Is it fine? So we want to look at it. We want to consider a point where you throw a body. Please try. Some of these things, however much I want to let you understand, but you must participate practically. I don't want to come with a stone and I start throwing. I throw a stone, I turn the camera. By the time I turn the camera, it has already reached the ground. So this one, you must do it yourself. Try throwing a stone at different angles. Try when the angle is very big, it falls near. Reduce the angle, it falls further. Reduce the angle, falls further. Time comes when you reduce the angle, it now comes near. So there is a point when you throw at a very certain angle, it falls the farthest. So this point is what you call the maximum range. That's the distance covered is the maximum range, and the angle is the angle corresponding to that maximum range. The diagram is there in the notes. You check it and go through it. I think it's down under the equation of trajectory. But this diagram is there, and the explanation is there for this. So ours here is, how do we get the maximum horizontal distance covered? How do we get the maximum range? We get the maximum range when sine 2 theta is maximum. And the maximum value of sine 2 theta is a 1. That's the maximum value of a sine. Maximum value of a sine is a 1. When do we get 1? We get 1 when 2 theta is 90 degrees. Am I right? How do you get sine 2 theta equals 1? You get it when 2 theta is 90 degrees. Plus sine 90 is what?
1.
Teacher, I haven't understood that part.
This one?
Yes.
If you want to get the maximum value of this equation, I hope you can see this equation. If you want to get the maximum value of this equation, then the condition is that keeping u constant and acceleration to gravity constant, what changes is the angle. So if it is the angle that changes, then try to maximize the sine 2 theta as maximum as possible. So for you to get maximum R, sine 2 theta must be maximum. How do you maximize the sine 2 theta?
Yes.
You maximize the sine 2 theta, the maximum value of sine 2 theta is a 1. That one you learn. Now, how do we achieve a 1 from sine 2 theta? We achieve a 1 from sine 2 theta when 2 theta is 90 degrees. You get the angle, you get sine theta equals 190 degrees. So I can get the maximum, which is a 1, when 2 theta is 90. And that means theta alone is what? Theta alone is 45 degrees, not so?
Yes.
Theta alone is 45 degrees. So we are winding up. So now this one. Yes? So this means that the angle corresponding to maximum range is 45 degrees. And we have just said that maximum range is obtained when sine 2 theta is a 1. So the maximum range is u squared out of g. That's the formula for maximum range. We obtain it when sine 2 theta is a 1. And I realize that when sine theta is a 1, theta is 45 degrees. Is that okay?
Yes.
Okay. Now, time has not allowed us to go through an example, but I want to leave it as an exercise that you do. Find for me, you write it somewhere. Pardon?
Go on, teacher.
You are going to find for me, the time taken to reach maximum height. You find the maximum height itself. You find the time of flight. And you find the range. Not maximum range, but you just find the range. Find for me those 4 when initial velocity is 25 meters per second and my angle theta is 60 degrees. Have you got the question?
What is u?
U is the initial velocity.
No.
25 meters per second.
Can you repeat the question, please?
The question is, find the maximum height. Find to reach max. Find the time of flight. And then find the horizontal range or horizontal distance covered.
So what is u?
What is what?
U.
U is meters per second.
The value?
The other value is angle theta 60 degrees.
Bye.
Okay, we can stop there.
Okay, teacher.
Thank you, teacher.
Okay, thank you so much.
The rest is in the work. You go through
Thank
the
you,
work.
teacher.
The rest is
Bye.